Statistical variance uses numerical data to make inferences from a sample. When applied to schedule performance, it can set plausible high and low bounds for estimated duration. The bounds, along with the nominal estimate at complete for time, are useful for decision-making on a project. Calculation of plausible high and low bounds is founded on building blocks. They come from earned value management and statistical analysis. From earned value management, get the plan value, get the earned value, calculate the earned schedule, calculate the schedule performance index for time, and here we need both the cumulative and periodic amounts. Historical SPIT is the basis for statistical analysis, but a study of periodic SPIT from real projects revealed a problem. To show the problem, I need more room on the screen, so if you want a closer look at the figures, pause the video now. Otherwise, I'm going to scroll the video. Here's a graph of the SPIT from the real projects. That's the wrong shape for the most common statistical techniques. But SPIT can be transformed mathematically so that the graph looks like this. How is that done? An analogy explains how. Consider the number 6. Used on a check, it's expressed as 6.00, a decimal number. Used in a computer, it's transformed into 110, a binary number. The numbers look very different, but they mean the same thing, 6. For SPIT, a mathematical function called the natural log does the transformation. It has these results. The SPIT and the log of the SPIT look very different, both numerically and graphically. But they mean the same thing, the same schedule efficiency. Once transformed, the SPIT data is in a bell-shaped curve. That supports common statistical techniques such as sample mean, sample variance, and sample standard deviation. Let's start with the mean. To calculate the mean, and the symbol for the mean is x bar, we sum the measurements, represented by x, and divide by the number of measurements, n. Remember, we're making inferences from a sample, so we need to subtract 1 from the number of measurements. Which measurements? The periodic values represent SPIT at a single point in time, rather than an accumulation, and that's the best fit here. Applying the formula to the example gives us these means. Note that there's no mean for the first period. That's because the divisor in that period is 1 minus 1, that is 0. Next, calculate sample variance. It looks like this. It's the variation on either side of the mean. Its symbol is S. To calculate S, first find the difference between each measurement and the current mean. At period 3, the values of x are minus 0.043, 0, and 0.118, and the mean is 0.038. Here are the differences. Next, sum the differences. Hold on, the differences can be plus or minus. A mix of signs cancels value. It's too early to do the sum. We want the differences regardless of sign. So, square each difference. If we square the right side, we have to square the left side as well. Here are the squares. Now we can sum the differences. And that gives us, finally, divide by the number of measurements, less 1. And that gives us, applying the formula to the other periods in our example, sample variance is useful in calculating the bounds, but the squaring makes it difficult to understand. How so? Here's another analogy. Say the measurements were not of SPIT, but instead were of time, say hours. The variance would then be square hours. It's a bit difficult to understand square hour, let alone plot it on a graph. But there's an easy way to solve the problem. Take the square root. Square hours becomes simply hours. The deviation then would be in hours from the mean. That standardizes the deviation by setting it to the same units as the original measurements. And that's why it's called the standard deviation. It's the square root of the variance. Applying it to the SPIT as of period 7, with a mean of 0.154 and a deviation of 0.250, we have a spread from minus 0.404 to plus 0.096. Is that the range of plausible values? No, that's the average dispersion around the mean. There are measurements here and here and here and here, but also outliers out here and out here and out here. To know plausible bounds, we need a better idea of the distribution of measurements under the curve. How far is each measurement from the mean? The standard deviation can tell us that. It gives us the last of the building blocks, the normal score. It's called that because bell-shaped curves like this one are called normal curves. Under that curve, the total area is, by definition, 100%. But that area includes outliers, and they are not likely values. So we'll exclude them. Say we only want measurements within 95% of the area under the curve. Because it's bell-shaped, we know that 95% of the area will be distributed roughly like this. It has 47.5% of the area on either side of the mean. We can calculate the distance from the mean for any individual measurement. The distance is measured in units of standard deviation. Take, for example, this point right here. The math for calculating that distance is involved, but we can approximate the distance with geometry. Imagine a triangle on top of the bell-shaped curve. Note that this is only an approximation and it only works for this case. We know that the total area under the curve equals 100%, and the area is divided into two equal parts. So the maximum height of the curve is 50%, and the triangle has the same height. The triangle's area is approximated at 47.5%. Using the formula for a triangle and solving for the base, we have this. The distance is about 2 standard deviations from the mean. More precisely, the normal score is 1.96 standard deviations away. The calculation of 1.96 is so involved that tables were created to hold pre-calculated results for common percentages such as 95%. To get a score today, we use computers and software. What's neat is that if you have a score, you can reverse the process. You can infer the area under the curve given the score. We'll use a score in the next video. There, we use the building blocks to construct plausible bounds for duration estimates. For now, let's review the building blocks. High and low bounds for duration estimates are based on historical schedule performance. Schedule performance is expressed by SPIT, but it has the wrong shape for statistical analysis. The log of the SPIT has the right shape. Find the sample mean, the sample variance, the sample standard deviation. Finally, find the score. For more information on Earned Schedule topics, here are some references.